One of the most important ways of improving performance in any modern application is concurrent execution. There are two contributing factors to this. One is that many tasks, like processing requests, processing data in a data store or data structure, and performing background work, can be easily and reasonably parallelized. The other factor is the existence of multiple cores and multiple CPUs on modern machines. Since version 1, Java has supported concurrent execution via multi-thread programming. In earlier versions of Java, we have the thread class for initiating and managing threaded execution, the synchronized keyword for obtaining and releasing locks, and the wait, notify, and notify all object methods for thread coordination. Over time, Java has built on these primitives and currently offers higher-level objects like the executor service and parallel streams for initiating and managing threaded execution, the lock class for obtaining and releasing locks, and thread coordination classes like the condition, semaphore, countdown latch, and cyclic barrier classes. In addition to these, we also have atomic variables, concurrent collections, and concurrent queues that provide additional synchronization functions. These higher-level classes are designed to take out some of the difficulty of writing concurrent code. However, even with these tools, it's still easy enough to write concurrent code that's inefficient or not as efficient as it could be. Knowing which concurrency option to use compared to another, how to use and configure these tools, and how to avoid certain pitfalls can be a challenge. And while it's not my intention to attempt to cover everything, in this module, we'll examine some of the best practices for working with concurrency in order to maximize the efficiency of your application. We'll start with a discussion of thread pools. We'll talk about how to size them and how to configure the work queue. Then we'll discuss a different type of thread pool called the fork join pool. We'll examine its properties, its use cases, and its advantages. Next, we'll look at ways to reduce lock contention. Topics to be covered here include reducing the scope of the lock and the use of lock splitting and striping techniques. We'll also look at another approach to reducing lock contention, which is the use of alternative coordination mechanisms like atomics and concurrent collections. We'll learn what situations are best suited for the different atomics and concurrent collections. And finally, we'll look at ways to rewrite our applications to have little or no synchronization. These include the use of thread locals, immutable objects, and a volatile keyword. So let's get started with thread pools. The most popular method for executing tasks concurrently in Java applications today is the ThreadPoolExecutor. The general concept behind thread pools is that there's some work to be done that's queued up, and a number of threads that can be used to execute the tasks. A thread picks up a task from a queue, executes it, and returns to the pool when the task is completed. While it's sitting in the pool, it's in an idle state, waiting for tasks to execute. One of the key considerations when it comes to configuring a ThreadPoolExecutor is the size of the pool. This is important because if the pool size is too small, then you may not be taking full advantage of your hardware to achieve the best possible performance. This graph shows the performance of a CPU-bound test application that was run with a varying thread pool size. On my machine with 8 cores available, the performance of the code increases as the number of threads increases. However, the flip side is also true. Setting the pool size to a value that's too high can have a negative impact on performance. There are several reasons for this. One is that the higher the number of threads in a system, the more time the CPU has to devote to scheduling threads instead of just running them. Also, switching from one thread to another involves saving the outgoing thread's context and restoring the incoming thread's context, which is an expensive process. And finally, context switching leads to invalidating caches and data locality that was built up for the previously running thread. Therefore, getting the pool size right is an important tuning parameter for thread pools. However, it's important to note that tuning the size of thread pools is not an exact science. And like many topics in the practice of performance optimization, you must find a balance between the performance gains resulting from getting the thread pool to its optimal size and the costs of constant tuning. There are two common approaches for determining the optimal pool size. One approach is to follow a formulaic model based on the number of available CPU cores, the target CPU utilization, and the characteristics of the task that's being performed. The other approach is more of an experimental approach, where the system is put on the load and different thread pool size values are benchmarked until the optimal size is found. With the formulaic approach, a model espoused by Java language architect Brian Getz in his book Java Concurrency in Practice is this one, where the number of threads is determined by the number of available CPU cores, multiplied by the desired CPU utilization, multiplied by 1 plus the ratio of wait time to compute time. This means that if you have a compute-intensive task, that is, a task that's CPU-bound and has virtually zero wait time, and you'd like to optimize for 100% CPU utilization, you should set your thread pool size to the number of CPU cores. However, If you're targeting 60% of CPU utilization, then you should set your thread pool size to 60% of the number of cores. For mixed or I/O intensive workloads, you would need to determine the average weight to compute ratio. If the weight to compute ratio is 75 to 25, and you're targeting 100% CPU utilization, then the number of threads should be set to the number of cores multiplied by 4. If you want to take the formulaic approach, you don't have to strictly use the guts model. You can start with the model and then tweak the results based on your hardware and application characteristics. You can tweak the formula itself and use different coefficients. Or you can use any model of your choosing that considers the factors that are pertinent to your application. Some of the factors, other than CPU, that can affect thread pool sizing are memory, file or socket handles, and database connections. The other approach to thread pool sizing is the experimental approach. With the experimental approach, you would subject the application to the volume and types of traffic you expect to handle, and then vary the thread pool sizes while monitoring system performance and thread pool characteristics such as the number of busy and idle threads and the length of the work queue. After enough iterations, the optimal thread pool size should emerge. Regardless of which approach you decide to use for thread pool sizing, for important thread pools, it's still beneficial to monitor thread pool behavior. Also, due to the nature of thread pool sizing, a best practice for doing so is not to hard-code the thread sizes into your code, but instead to make it configurable using some configuration method like a config file, or to dynamically calculate it based on the runtime.availableProcessors method. Another recommendation is that for a task that has both CPU and I/O bound components, if it can be cleanly and efficiently done, it might be beneficial to split the task and use different thread pools that can be individually sized and tweaked. Lastly, if you have multiple thread pools in your application, focus first on tuning your core or critical thread pools, like your service or data layer thread pools, before tuning auxiliary thread pools for functions like logging. When creating a ThreadPoolExecutor instance in Java, you configure the executor with a core pool size, a max pool size, a keep alive time, and a working queue instance. The core pool size is the number of worker threads that will be kept in the pool for executing tasks. When tasks arrive in the pool, they are queued and then picked up by an idle worker thread. If all the threads are busy, then the task stays in the queue. There are 3 different types of queues: unbounded queues, bounded queues, and synchronous queues. When an unbounded queue is used in an executor, the pool size never changes. As the queue grows, the latency of your application grows, as tasks in the back of the queue must wait for all preceding tasks to be executed first. And if your clients are throwing requests faster than the server can handle, you will run the risk of exhausting the resources of your server. If you have a bound queue instead, when the queue is full, the thread pool adds a new worker for handling tasks up until a maximum number of worker threads, and afterwards it starts rejecting requests. For many server applications, a best practice is to correctly size your pool. Use a bounded queue with a limit that's relatively small but just large enough to handle bursts of requests, and to set the core and max number of workers to the same size, or the core pool size to the bottom range of your optimal size calculation, and the max pool size to the top range. One last thing to mention is the choice of queue implementation. The typical first in first out bounded queues, like linked blocking queue and array blocking queue, cause tasks to be started in the order in which they were received. If you have some tasks that are more important than others, you can instead use a priority blocking queue, which would order tasks by priority. Introduced in Java 7, the fork join pool is an executor service implementation that's designed for tasks that need to be split up into smaller chunks, which can then be executed in parallel. The canonical example of such a task is having to sort an array with millions of items. The fork join pool uses the paradigm of recursion to accomplish the splitting and merging. If a task is larger than a certain threshold, it gets split over and over again until it's under the threshold, at which point it actually gets executed by one of the threads in the thread pool. This is the fork phase. Tasks that get split into subtasks are suspended until their subtasks are completed. When the subtasks are completed, the results are merged in the join phase to form the final result. Here's an example of a recursive task. If the task size is above the threshold, we are creating 2 new instances of the recursive task and calling fork on each. This places the task in the queue, where it will wait to be picked up by a free worker thread. Next, I have the join statements, which tell the tasks to wait if necessary for the results of the task. When the task is below the threshold, then it gets executed directly, and the results get returned to the caller, which is either the waiting parent task or the client itself. As an aside, note that if you have no return value, you can use the recursive action instead of a recursive task and skip the join portion of the code. Once you've defined your task, you can either create an instance of a fork join pool with a specified number of threads, or use the common fork join pool provided by Java and call the invoke method. This is a highly contrived toy example just to illustrate the mechanics of the fork join pool. A more concrete example would be a service where the user submits a variable number of items to process. You can use the fork join framework to say that if the number of items is under a threshold, like 100 for example, then directly process it. Otherwise, break down the list into chunks of 100 and then process it. The advantage of the fork join pool is that with its unique recursive model, it can handle a large amount of tasks with very few threads. The Java 8 parallel streams feature uses the fork join pool under the hood to parallelize operations and collections. If it fits your use case, you should give the fork join pool a try. In Java, locks are used to protect shared state from data corruption when being accessed by multiple threads. When a thread obtains an exclusive lock, other threads trying to obtain the same lock must wait until the owning thread releases the lock. The blocked thread can either wait for the lock to be released by spin waiting, that is repeatedly trying to acquire the lock until it succeeds, or the thread can be suspended by the operating system. If the wait time is short, spin waiting might be more efficient than getting suspended, as it avoids the cost of context switching. However, with longer wait times, suspension is preferable. To implement blocking, the JVM may choose to start with a spin wait and then suspend the thread after a set number of spins. It may heuristically choose either spin waiting or thread suspension based on profiling data of how long the wait times are, or it might simply default to suspending blocked threads. This behavior may be configurable in your JVM. If you're inclined to do so, you may dig around your JVM flags to try to configure this. But my advice would be to avoid going down this path, and instead use other techniques for concurrency optimization. One important thing to note is that locks are not bad, lock contention is. When lock contention happens, only the winning thread can run. This means that you're reduced to serial execution instead of parallel execution, and the scalability of the code takes a hit. Lock contention also leads to context switches, which are expensive and hurt performance as they involve storing and restoring state, cache invalidation, and data locality misses. Locks are often classified based on how contented they are. A lock can either have high contention, sometimes called a fat or a hot lock, or it can have low contention or be uncontended, sometimes called a thin lock. Having a highly contended lock become an uncontended lock is not only desirable because it's much cheaper, but also the JVM can perform additional optimizations that can further reduce or eliminate the cost. If a lock in your application is low or uncontended, then you shouldn't bother optimizing the locking behavior any further. When it comes to concurrent code, it's especially important to heed the doctrine of avoiding premature optimization, or the mantra that says, first make it right, then make it fast if it's not fast enough already. This is because concurrent code is already difficult to reason about, and while some optimizations are simple and straightforward enough, many optimizations involve convoluting your code even more, leading to code that's expensive to maintain and error-prone or brittle. If you have hot locks, then there are 3 ways of reducing lock contention. These are reducing the duration for which the lock is held, reducing the frequency at which the lock is requested, and replacing locks with other mechanisms that allow for greater concurrency. We'll discuss alternative mechanisms in the next clip. For now, let's look at ways to accomplish the first 2. Reducing the duration for which a lock is held is simply a matter of reducing the size of the critical block to the point where only the shared data access is protected. In the example here, let's assume that multiple threads can call the updateScore method with different score implementations to calculate a score and update the value of the score field. In order to protect the score field from data corruption, you would synchronize access to the updateScore method. The problem here is that this creates a lock on this object that covers more than it needs to. The calculateScore method might be an expensive method, or even worse, it might involve I/O. In order to reduce the lock duration, you should instead have the lock only protect the data modification, like in the modified version of the code. There are a few techniques for reducing the demand for a lock. One of those is lock splitting. Lock splitting takes a single lock that's guarding different independent shared state variables and splits it into multiple locks for each variable. This diffuses the demand on the lock and results in each lock getting requested less frequently. In this server statistics class, the count of active users and the count of concurrent database queries are independent of one another. However, the current implementation uses the synchronize keyword on the accessor methods, which means that access to both variables are synchronized on the same statistics object. Having a lock for each variable will help combat lock contention in this case. Related to lock splitting, but with a different mechanism and goal in mind, is the use of the read-write lock. If a collection or data structure is written to infrequently, for example when it's initialized and when there are updates, but reads happen at a high frequency, then a read-write lock is ideal for reducing lock contention. Instead of having a single lock to protect some shared state, the read-write lock gives you two locks, the read lock and the write lock. Multiple reader threads can hold the read lock and run simultaneously as long as there's no writer thread holding the write lock. As soon as the writer thread obtains the write lock, the reader threads are blocked. With the write lock, only one writer thread can hold the write lock at a time. This pattern allows you to have higher throughput data structures as long as reads surpass writes. If writes surpass or last longer than reads, then the advantage of this pattern is lost, because the data structure will spend most of its time being locked exclusively. For examples of using read-write locks, you can check out the Java documentation on the web. The other technique for reducing the demand on the lock is lock striping. Lock striping, like lock splitting, reduces the granularity at which a lock is applied. Lock striping is applicable when we have a variable-sized collection of independent objects. With lock striping, you partition your data into groups, then have a lock for each group instead of a lock for the whole object. This is the approach used by some versions of concurrent hash map to allow concurrent writes to a single map. As long as each write is updating a bucket guarded by a different lock, then there's no lock contention and they can operate concurrently. We'll take a closer look at concurrent hash maps in the next clip, but first let's take a quick look at an example of how we can implement lock striping ourselves. Here we have an array of locks, and when we want to update a user's location, we use the user's ID to select one of the lock objects and then synchronize on that object. One thing to note is that the effectiveness of lock striping depends on the distribution of data. If the data is not well distributed, then the demand for locks can be concentrated on only a few hot locks. The last thing I want to quickly mention is that instead of using the synchronize keyword for locking, you can use a lock object from the java.util.concurrent package. The lock object provides some additional features, like being able to interrupt a thread that's waiting for a lock, and being able to set a timeout on the amount of time a thread waits for a lock. But the feature most pertinent to this discussion is that the implementation of the reentrant lock has been shown to be more scalable under high contention than the implementation of the synchronize keyword. At higher thread counts, explicit locks perform better. If you only need to synchronize access to a single variable, then instead of using a lock, you should use an atomic variable instead. Java provides the atomic boolean, atomic integer and atomic integer array, atomic long and atomic long array, and the atomic reference and atomic reference array classes. Objects of these classes allow you to set their values atomically. In the case of atomic integer and atomic long, perform simple arithmetic operations such as increment and get, decrement and get and add that can be done atomically. The significance of these operations being atomic is that because they can happen in one step, thread interference, which leads to data corruption, cannot occur. Therefore, when atomic variables are used to synchronize access to shared state, locking and the costs associated with threads being blocked are eliminated. The implementation of atomic variables rely on hardware support. Atomic variables use the atomic compare and swap instruction that's been provided by most modern CPUs since 2013. If the compare and swap instruction is not available, then the operating system may fall back to a lightweight locking mechanism like spin locking. Atomic variables generally outperform lock-based synchronization, and often by a lot. Therefore, in general, it's advisable to replace synchronized access to a single variable with the atomic variant of the variable. For example, in the score example from the previous clip, we can replace the score variable with an atomic long and get rid of the synchronized block. If we want to get the value as a double later, we can use the atomic long's double value method. There's a situation where we can employ an even faster data structure than an atomic long or atomic integer. And that's when we have very frequent simultaneous writes by multiple threads, which leads to high contention for the atomic operation. In Java 8, the long adder, long accumulator, double adder, and double accumulator classes were added. The long adder is internally composed of cells that each contain a variant of atomic long. If a thread tries to update the value of a long adder, while another thread is currently executing the compare and set operation, instead of waiting, the thread selects another cell to add its value to. The effect of this is that under high contention, writes is spread across various cells, which reduces the contention and increases the throughput. To get the total value of the long adder, the values of all the cells are collected and added up. Here, I'm replacing my locked active user count variable in the server statistics class with a long adder which will perform much better under high write loads from multiple threads. One small thing to keep in mind is that long adders require more memory than atomic longs or synchronized variables due to the fact that it contains multiple internal cells. The Java.util concurrent package provides a number of concurrent collections, but the two that I'll focus on are the concurrent hash map and the CopyOnWriteArrayList. The concurrent hash map is a thread-safe version of the hash map data structure that supports highly concurrent updates and fully concurrent retrievals. Earlier implementations of the concurrent hash map used lock striping to enable high concurrency. As a result, they provided much better performance and scalability than a collections.synchronize map or a hash table, which both use a single lock to guard the entire object. In the current OpenJDK implementation of concurrent hash map, these locks have been dropped in favor of compare and swap operations and volatile puts and gets with locking limited to just the node level. As a result, current implementations have even greater performance and scalability characteristics. Concurrent hash maps are a drop-in replacement for synchronized maps. The other commonly used member of the Java.util concurrent package is the CopyOnWriteArrayList. The CopyOnWriteArrayList ensures thread safety by creating a copy of the underlying array anytime a mutative operation like add, set, or remove takes place. This guarantees that for threads that are currently iterating through the array list, the array object they are iterating won't change out under them. The alternative to this will be to use a synchronized list, which places a lock on the list in order to ensure stable iteration, but with the CopyOnWriteList, no locking is needed. When a new reader thread comes in, it gets an iterator that points to the current state of the underlying array. Any subsequent additions, removals, or updates will not be visible to it. The result of this model is that the CopyOnWriteArrayList is highly inefficient if there are lots of updates to the list or when the list is very large. But if there are very few updates and list reversal operations vastly outnumber update operations, the CopyOnWriteArrayList can be more efficient than a synchronized list. If the CopyOnWriteArrayList doesn't fit your use case, you would like to avoid using a single lock over the entire list, and you don't need index-based access or the ability to add in the middle of the list, then you could look into using a concurrent linked queue instead. The concurrent linked queue uses a non-blocking compare and swap operation for adding and removing items from the collection. It also implements the iterable interface so that you can loop over its contents with the enhanced for loop. While the previous two clips have talked about ways to reduce lock contention and use lighter weight means of synchronization, there are some instances when it's possible to avoid synchronization altogether. An example of that is when you can replace synchronization with the volatile keyword. Applying the volatile keyword to a field lets the compiler in the Java runtime know that this variable is shared. For the compiler, this means that it should not reorder operations to surround this variable. While for the runtime, this means that volatile variables are not cached in registers or processor caches. Instead, they are written directly to and read from memory. In addition, when a thread writes to a volatile variable, all variables visible to that thread are also flushed from cache to main memory. The effect of all this is that when you have a volatile variable, updates from one thread are predictably propagated to other threads. The most common usage of volatile variables is as a completion, interruption, or status flag. However, the use of volatile can extend to any situation where updates are being done by only one thread and you have one or more reader threads. You can also use volatiles if you have multiple writer threads, but writes to the variable do not depend on its current value, which means that the writer threads are just publishing the results. When we're dealing with shared objects, one thing to note is that immutable objects do not need synchronized access. Immutable objects are objects which, once constructed, their state cannot be changed. That means that data corruption cannot happen, hence synchronization is not needed. Therefore, the more you use immutable classes when writing concurrent code, the less synchronization and locking is needed. The last workaround for synchronization that I'll discuss is not sharing at all. Instead of sharing an object amongst threads, you can have each thread have their own copy using the thread local class. In the example here, we have a serializer object that's not thread safe. So instead of serializing access when using it for multiple threads, I can use a thread local object instead. Every time a thread calls cryoserializers.get, it gets its own copy of the serializer object, and there's never any shared access, synchronization, or thread contention. If you can rewrite your application to avoid synchronization, then you should obviously do it. However, there are instances where you've completely paralyzed your workload, each worker has its own resources, and nothing is shared. But at the end of the task, you need to gather all the results back together to pass back to the user or to pass on to the next stage of the process. Aside from concurrent collections, One of the ways you can do this is to use a concurrent queue implementation. There are two variations of these, a set of queues that are non-blocking and a set that are. The utility of the blocking versions is when you want the consuming thread to wait for a period of time for a message to arrive in the queue, or if you want to control the growth rate of the queue. Either way, concurrent queues are a great way to delay or push synchronization to the edges of your tasks. This is where we'll end our exploration of concurrency optimization techniques. Although we breezed through a lot of fairly complex topics, there are lots of resources on the web and in excellent books like Java Concurrency in Practice and Java Performance the Definitive Guide that allow you to dive deeper. In the next module, we'll start wrapping up the course.